Newton's three laws of motion don't actually mention principles such as the conservation of angular momentum or the conservation of energy. Instead, principles such as these are just a consequence derived from applying Newton's three laws of motion and the laws for how forces are generated. Consider a system consisting of two spheres of equal mass, connected by a spring, rotating in space with no gravity present. The yellow arrows are vectors representing the momentum. The red arrows are vectors representing the forces on the spheres. In this scenario with the two spheres, the stretching and compressing of the spring can only cause the spheres to either feel a force directly towards the center of rotation or to feel a force directly away from the center of rotation. The length of each yellow arrow is equal to the momentum of each sphere. The angular momentum of each sphere is equal to the area of each blue rectangle. Angular momentum must be conserved, which means that the area of each blue rectangle must stay constant. When the two spheres are moved closer together, the length of each yellow arrow needs to grow to keep the area of each blue rectangle constant. When the yellow arrows grow, the velocity of each sphere is increased. When the two spheres are moved further apart, the length of each yellow arrow needs to shrink to keep the area of each blue rectangle constant. When the yellow arrows shrink, the velocity of each sphere is reduced. But how do the yellow arrows know that they need to grow or to shrink? The yellow arrows are vectors representing the momentum. The red arrows are vectors representing the forces on the spheres. Isaac Newton originally expressed his second law of motion by stating that the force on an object is equal to the rate at which its momentum changes. One of the consequences of Newton's second law of motion is that for an object to follow a circular motion, the object requires a constant force towards the center of the circle. The force has to be just the right magnitude so that the momentum vector keeps changing its direction, but not its length. Suppose that this force towards the center is always present. Suppose we move the sphere further away from the center by adding a brief extra force away from the center. This force causes the sphere to have less linear velocity in the direction of the rotation. For the sphere to move closer to the center, it requires an extra force towards the center. This causes the sphere to have a greater linear velocity in the direction of the rotation. Hence, the sphere ends up rotating around the center at a higher linear velocity. Therefore, even if we had never heard of the conservation of angular momentum, we can explain the change in velocities based entirely on the forces and Newton's second law of motion. Much more information is available in the video, Momentum and Angular Momentum of the Universe. Please subscribe for notifications when new videos are present. Special thanks to all the people supporting us on Patreon. Your support is very much appreciated.